where we left off, which is number 10. I presume that's what you want to do?
Yeah.
There are three main equations whenever you're doing compounding. Okay, the first one is this one. Second one is this one. This is when it's more frequently than annual. And the third one is this one, for continuous. All right? If you want to memorize any three things, memorize these three. And know what each variable is. In other words, the a on the left side of the equation is the amount that it will be equal to at the end of the period, whatever time you want to select. Well, this problem, Omar is 8 years old and he received 25,000. What number is 25,000 in these equations?
It's the starting amount.
The ace of 1. That's what ace of 1 means, is whatever you start with. Hold on a minute. Let me make sure. Okay. So his father invested it for him in a fund that earns 6% annual interest compounded quarterly. Now, which equation are we to use? The top, middle, or bottom?
The middle.
Good. What's R?
365.
No.
Or
In other words, we're using this equation. Ace of 1 we know is 25,000. R is the interest rate, 6%. Only you have to write it as 0.06. In other words, you almost never want to put a percentage in an equation. You want to convert it to a decimal. Okay? So the specific equation for this is 25,000 times 1 plus R is 0.06. What is N? If it's compounded quarterly, what does that mean?
every 3 months.
So 4 times a year. That's what N is the number of times per year. So N is 4, and it's to the NT, so it's to the 4T. Okay?
Yeah.
Now we have an equation, notice, that you give me a time and I can figure out what A is, no matter what period of time you give me. Or if you give me an A, I can figure out what period of time that requires. So if we read the rest of the problem, he was hoping to see his investment double by the time he's ready for college. Well, first of all, write an equation to represent each situation. Well, that's our first equation. That represents the situation where he's earning 6% annual interest compounded quarterly. You with me?
Yeah.
Okay. Now, another fund is what they meant. Not fun, but fund. Offered the same interest rate, but the interest would compound continuously. So tell me what that equation would be.
The third one.
Okay, fill in the blanks.
Given, right, A equals 25,000. And then 0.06.
E, you don't need to turn that into a number. It's like pi. It's most accurate when written as E.
Yeah.
So it's e to the power of 0.06 t. Okay?
Oh.
And that's the second equation. So there's the answer for A, 10A, or those two equations. Notice that both equations, the only variable is t, really. In other words, the amount you're going to make is going to be a function of t, and in the second one, the amount that it's going to be worth is also a function of t. Which method of compounding the interest will double his money faster? Well, let's talk about two things. First of all, if the interest rate is the same, then continuous compounding is always better than any other method.
Okay.
And in fact, if you were to prioritize these, that's the worst, that's the next worst, that's always the best. So which method will double his money faster has to be the second equation, because they didn't change the interest rate. The interest rate stayed at 6%. They could have made it a little interesting if they'd have said 5.9%. But if they're giving you the same interest rate, well then continuous compounding always is better than non-continuous. Now, this question about doubling. We answered A. Which method of compounding the interest will double his money faster? Well, I told you that continuous compounding was faster than the quarterly compounding, but let's prove it. In other words, how long, let's figure out how long it's going to take to double his money with the first method.
Okay.
Well, what's A going to be?
50,000.
So I got 50,000 equals 25,000 times 1 plus 0.06 divided by 4 times 4 to the t. Now, whenever the variable, and there's only one variable here, it's t. Whenever the variable is in the exponent, then you're going to have to use logarithms to solve it, always. If the variable is not in the exponent, then you probably don't have to use logarithms to solve it. But even using logarithms, what's the first step?
Dividing 50,000 by 25,000.
So I get 2 equals 1 plus, if I do this division, that is 0.015 to the 4t, which means 2 is equal to 1.015 to the 4t. You with me?
Yeah.
In other words, you always want to add these two numbers together. Now, in order to solve that, as to how much time it'll take to double your money, this is not an algebraic equation. This is an exponential equation. And the only way to solve exponential equations, even on your calculator, you would not be able to solve this on your calculator if you did not know about logarithms. But we do know about logarithms. So I'm going to take the log of both sides. Now, once I've put it into a logarithm equation, that allows me to use the rules of logs to bring this variable here, 4t, down on the algebra line, like this. That's the beauty of logs, is it lets you take a number that's in the exponent and put it on the algebra line. And now you can probably see that t is going to solve to be natural log of 2, and that number is just precisely that. It's a number. That's all it is. You can get it out of your calculator. But the fact is, if I'm solving for t, I got to divide both sides of the equation by 4 and times that number.
Okay.
Now, that's what t is. And that number you can get out of your calculator. And that's the only place to get it. None of us know how to do natural log of 2 or the natural log of this other number. So it's always a question of looking it up in a table or a calculator, and that will give you t. Now, let's go back and figure out what the amount of time would be if we use continuous compounding. And then that will prove which one is the quicker. Okay? I mean, you kind of had to take my word for it when I told you continuous compounding is always better than quarterly compounding. But we can prove it by solving it. So again, A is going to be 50,000, and I'm going to divide both sides by 25,000. So in this case, I get 2 equals e to the 0.06t. Again, I have an exponential equation I have to solve, so I'm going to take the log of both sides, and I always use natural log. And in this case, natural log actually is quite helpful because the natural log of e is 1. So now t is going to be equal, since that's 1, t is going to be natural log of 2 divided by 0.06. So there's the amount of time it would take to double the money under continuous compounding. There's the amount of time it would take to double under quarterly compounding. And the only way you can really prove which one is smaller is by coming up with these numbers. In other words, figure out what natural log of 2 divided by 0.06 is. Do you have your calculator?
Yeah.
It's a TI-84 or a TI Inspire?
84.
Well, you've got a natural log key in there. So let's figure out what natural log of 2 divided by 0.06 is.
Okay. 11.55.
So 11.55 years to double the money with quarterly compounding. Excuse me, with continuous compounding. Now, in your calculator, figure out what natural log divided by 4 times natural log of 1.015 is. And be very careful how you put this in. Make sure you use plenty of parentheses. In other words, you need parentheses on the outside. You probably need parentheses on the inside, like that, maybe even on that. I don't know. With a TI-84, it's hard to put these things in because if you don't get your parentheses right, it's not giving you the right answer. And it doesn't tell you what you did wrong. So you have to be very careful here.
I got 11.64.
Perfect. I know that that is correct merely because I know that continuous compounding is better than quarterly, but not that much better. Just marginally better. In other words, with continuous compounding, I doubled my money in 11.55 years. With quarterly compounding, I doubled it in 11.64 years. Obviously, you'd rather use continuous.
Okay.
Okay. Now, these three functions that I wrote at the beginning are really important. I mean, we're looking at 4 or 5 questions here that all deal with these three functions. Question number 10 deals with just the second and the third. Doesn't deal with the first. But question 11 does deal with the first. So let me leave those there for the moment and erase. Hold on. You don't want to get rid of those because we're going to need them. But I don't need all this stuff. So if we look at question 11, somebody's investing $2,400 at 12% interest. They don't say, oh, okay, what's the value after 20 years if it's invested with annual, monthly, quarterly, or continuously? So there's 4 possibilities. So let's figure out the annual. Annual would be what? A equals what?
2,400. And in parentheses, 1.12 to the power of t.
Which in this case is 20.
Yeah.
Okay. You have your calculator. Do you know how to take 1.12 to the power of 20?
Yeah.
Go ahead and do it, and then multiply that by 2,400.
Um, 23,151.10.
All right, that's close enough. All right, now let's do it monthly. Which equation do we use of the top 3?
The second one.
Okay, fill it in for me.
Yeah. 2,400, and then times 1 plus 0.12 divided by 12 to the power of 12 or of 12t.
Which 12 times 20. Okay, let's get an answer on that. Hold on a minute. Back up. Let me erase all this other stuff here. You have your calculator? Andy, you're going to need to come up with a number on this. In other words, 12 times 20 is 240. So let's just do that. And go ahead and come up with a number on that.
It's 1.01 is 0.12 divided by 12 plus 1.
Yep.
So the total would be 26,142.13.
Okay, very informative. That tells us that monthly is a lot better than annual. I mean, that's quite a bit more. That's almost $3,000 more. Okay. Now, hold on a second. What happened to quarterly? Wasn't that one of the choices? Oh, that's the next one. Okay. Hold on. So, give me the equation for quarterly.
2,400 times 1 plus 0.12 divided by 4.
And I would always do that step. Don't ever try to do that in your head. You're just asking for errors.
Okay. And then to the power of 4 times 20, or 80.
Okay. Let's go ahead and get that number. This should be worse than monthly. Monthly is better than quarterly. Quarterly is compounding only 4 times a year. Well, monthly is more often. It's 12 times a year. So this number should be less than 26,142.
Okay, 25,538.14.
Okay. And finally, continuous. Give me the equation for continuous with everything plugged in.
2,400 e to the power of 0.12 times 20.
Okay, good. 0.12 times 20 is 2.4. So let me erase that and write 2.4. Now it's a little easier. Come up with that number. That should be the biggest number yet.
Uh, 26,455.62.
Now notice that the last one was just barely better than monthly, which was barely better than quarterly, but all of them were better than annual by quite a bit. The annual was 23,151. Okay. Now, here's the point of fact. In nature, everything is continuously. The only places you get annual, monthly, quarterly, stuff like that is human creations like bank accounts. In other words, a bank will decide to pay you annual interest. Or some bank, the bank across the street from the first bank, may say, well, I'm going to pay them the same rate of interest, only I'm going to compound it monthly. That's a lot better for the consumer. But nothing in nature works on an annual, monthly, or quarterly basis. Everything in nature actually works on a continuous basis. And by that I mean if you have bacteria multiplying in a petri dish, it's going to be continuous compounding. If you have radioactive plutonium that is decaying in a petri dish, you have continuous decay, where R is merely negative. Every process in nature is continuous in form. So the only time you're ever going to encounter the annual, monthly, and quarterly is when you're talking about bank accounts, and sometimes maybe when they're talking about depreciation of cars, which isn't actually annual, it's continuous, but they like to treat it as annual sometimes. So the human creations are what create the first two formulas. The formula, if you want to remember a formula for real life, it's this one right here. Everything is continuous. Okay?
Okay.
All right. Let's go to 12. Compounded monthly. Give me the equation that's going to apply. Give me the general equation.
Okay. So it equals the first term, then a 1 plus the percent of like how compounded percent over.
Well, 12% is the number 0.12.
Yeah.
Okay.
And then divided by 12 because monthly. And to the power of 12t.
Okay, good. Now, that's the general formula. Well, that would actually have been R. But the specific formula is 10 thousandths, the initial amount. This ends up being 1.01 to the 12t. And they said the account now contains 30,000. So that's what now means, is whatever A is. Okay? So
Okay.
how long ago did she start the account? Well, the way I'm going to solve this is substitute 30,000 for A. That's equal to 10,000 times 1.0112t. Very first thing to notice, there's only one variable in that. Means you can solve it. There aren't two variables. Second thing to notice is that the variable is in the exponent. It means we're going to have to use logs to solve it. It's the first step.
Divide 30,000 by 10, which equals 3.
It's the next step.
You take the logs of both sides.
What kind of log?
Natural.
You can actually take any log you want. It does not matter whether you take the natural log, the common log, or the log base 3. I always use natural log just because once you get into calculus, that's the log you always use is natural log. And so I just kind of as a force of habit use it. Your calculator only has two keys on it, common log and natural log. So you want to use one of those. Okay? Now what? How does that help me solve for t?
You can put the 12t in front of the natural log on the right side.
Yeah, now this is a little different than we're used to. In other words, that is just a number. But the fact is, it's after the t, not before. And usually our numbers are coefficients. They're before the t. But in this case, they're not. In other words, so what is t going to be? Not the exact number, but, well, actually I do mean the exact number. But I don't mean as a decimal. I mean in logarithmic expression.
The natural log of 3 divided by 12 times the natural log of 1.01.
Now that number you can get out of your calculator. And that's the number they're looking for. Now, in point of fact, you could probably give this as an answer. In fact, if I were the teacher, this is my best answer. This is precise. There is no approximation going on here. Whereas if you convert this to a decimal, in other words, if you really want to know exactly how many years it takes your 12,000 or 10,000 to go to 30,000, well, then you probably want to convert this to a decimal. But if you want to know the precise answer, what I've circled is it. But usually these questions where they want to know time, then you want to give them time in years. So what is that number?
9.2 years.
And that makes sense. That you would increase your money by a factor of 3 in 9.2 years if you could earn 12% a year on it. And notice how astounding that is. 12% a year times 9 years is only 108%. And yet, because of the compounding, you're actually getting almost 3 times on your money. It's going from 10,000 to 30,000 in 9 years. That's not bad. And what that kind of tells you is that 12% is a great rate to earn on any money.
Okay.
Nobody pays that anymore. There was a time in my life where you could actually make 12% from a bank. But now you're lucky if you can get 2%. Interest rates have fallen so low that it's hard to even get 2% on your money. All right. Now, 13 kind of presupposes that we're talking about annual compounding. Even though it doesn't say that. And even though I've said that nothing in nature grows with annual compounding, which is the truth, but that's what they want you to use here. Because they didn't say continuous compounding. They just said that it's been growing at a rate of 2.4% every year since 2008. Okay? So what's the general equation as to what the current number of students is going to be?
1,600 times 1.024 to the power of t.
Well, okay. That's not really the general equation. That's the specific equation for this particular model. Okay? In other words, when I say what's the general equation is this. 1 plus r to the t power. That's the general equation. That's the equation that applies whenever you're doing annual compounding, no matter what the specific model is. But once you've plugged in everything, you get this. So this is called the specific equation. And it's the answer, well, it's not quite the answer to A. What is T?
10 years.
Well, how many years have taken place since 2008? If we were in 2009, what would T be?
1.
So you subtract the date, the years, right?
Yeah.
Well, we're in 2017. So what is T?
9.
Correct. So this is the exact specific equation that will tell you how many students there are after 9 years? Want to come up with that number? I'm presuming you need to answer this and turn it in. It's always a good idea to come up with the number anyway. Just because if you came up with a number like 2 million, you'd know you were doing something wrong. In other words, it's nice to come up with a number and then realize that, yeah, that's a reasonable ballpark number. I wouldn't expect the number to be 3,000. I wouldn't expect it certainly to be 1,000. Hold on 1 second, Nicholas. Hello? All right, sorry about that. So what number did you get?
1,980.
And that, again, makes sense. That, to me, is a ballpark number. And one of the secrets in math is to make sure you know what a ballpark number is. In other words, you know that it can't be less than 1,600, right? Because it's growing.
Mm-hmm.
And you know it's not growing at an outlandish rate. When we were compounding money, 2.4% is a very small growth rate. So it's not going to go to 16,000. It's not going to increase by a factor of 10. So increasing by a factor of about 24% makes perfect sense. Now, how many students will there be in 2018? Give me the equation.
1,600 times 1.024 to the power of 10.
Okay, go ahead and come up with that number.
2,028.
Okay. And finally, the trickiest one is how long will it take for the population to reach 3,000 students at this growth rate? We can actually go back to this one right here, this equation. How do I solve this? I want to know how long it's going to take for the amount to be 3,000.
You substitute 3,000 for A.
And now again, notice we have one equation and only one variable, which means I can solve for t. What am I going to have to use to solve for it?
Logarithms.
Always. If your variable is in the exponent, you're going to need to use logarithms. Now work me through the log solution of this.
So 3,000 divided by 1,600.
Which is the same as 30 divided by 16. Okay.
Equals 1.024 to the power of t.
Okay, next step.
30 divided by 16 is 1.875.
Hold on. Remember, at some point, you're going to have to take the logs of both sides.
Yeah.
This is the point. So when I say what's the next step, it's take the natural log of both sides. Remember, with equations, you can do anything you want to the left as long as you do it to the right. Okay?
Yeah.
Now tell me what the next line is.
Natural log of 30 divided by 16 equals t times natural log of 1.024.
Okay, so I'm going to bring the t down like that. Now what's the final thing for t?
Natural log of 30 divided by 16 divided by natural log of 1.024.
Okay. Go ahead and come up with a number if you want on that. Again, this is a little tricky to enter into your calculator. Make sure you use parentheses around that.
26.5 years.
Okay, and that makes sense. If you're only growing at 2.25% per year, and they have said how long is it going to take to double, well, 26 years, I mean, even if it wasn't compounded, it would be close. And compounding always makes it bigger. Okay, in other words, my quick and dirty check would be 2.4% times 26 years, right? Well,
Yeah.
what does that give you? 52 and 6, that gives you about 58%, which isn't double. But that's because that's not compounding. Is all I did was just multiply 2.4% times 26 years. If you compound it every year, then it does almost double in this 26 years. It goes from 1,600 to 3,000. So it's close to doubling in a lot less than you would think. So compounding definitely makes a difference, and it helps.
Okay.
All right, let's go to 14. All right, which means we're done with the 3 compounding equations. We're now into probability, combinatorics, and permutations. What's the answer to 14?
The answer?
Set it up. Don't give me a numerical answer. Give me the formula, equation, expression, whatever you want. The key word is choose.
It would be 10 choose 8.
Yep. How do you know how to do that?
Yeah.
What is that?
45.
Well, tell me what it is. It's 10 factorial.
Divided by 8 factorial.
Not just 8 factorial. 8 factorial times 2 factorial. And you apparently put all that in your calculator, and you got 45, okay, which is correct. But first of all, do you know how to do that without your calculator? It might be worth knowing.
Yeah, it's just like 10 times 9 times 8 times 7 all the way down, and then...
Okay, and then the bottom is going to be 8 times 7 times 6 all the way down times 2. Well, you can take that 8 all the way down and cross it off with that 8 all the way down, and we end up with 10 times 9, which is 90, divided by 2, and that's how you got 45. Okay? So even though you have a calculator function that lets you do combinatorics, it's occasionally good to know how you're going to do it if you had to do it without a calculator.
Okay.
Okay? Which we just did. Now, 15. We got 350 people running a race. How many different ways can they finish in first, second, and third? This is actually quite straightforward. How many different ways can let me see if I can figure out how to ask this. How many different people can finish first?
350.
Once first place is determined, how many people can finish second?
348.
49.
Or 49, sorry.
And then once first and second are decided, there's 348 that can finish third. Multiply those three together, and you get that's how many different ways. You can come up with a number if you want there.
42,508,200.
Okay. All right. Now let's go to more typical math problem. Let's see. We got about 13 minutes. Well, let's definitely do 16A. You know what these bars mean?
Absolute value.
Okay, what's the next step on this equation?
Add 7 to
Okay,
divide 7.
now I got the absolute value of 3x plus 4 equals 16. What two things does that mean? And that's the way you do all absolute value problems, is you always separate it into two different equations. Okay, well, this can mean two things. What's the first thing that it can mean?
3x plus 4 equals negative 16.
Well, let's start with just removing the absolute value sign. You never want to change what's inside the absolute value sign. Remember that. So what's the second thing it can mean?
3x plus 4 equals negative 16.
Right. In other words, is all you do is change the sign on this side of the equation. I get a lot of students that they're really intent upon making that negative 3x minus 4. In other words, they really want to change the inside. Don't ever change the inside. Now, it's very straightforward. You have two different equations you have to solve. What's x over here?
3.
Well, you're close, 4. Or, what's x over here?
5. Or
What's that?
it's 6 point.
And don't give it to me like that. That tells me you did it in a calculator. Give it to me as a ratio.
Negative 6 2/3.
Well, negative 20 divided by 3. That's the ratio that is the most meaningful to me. That is equal to the number you were giving me. But you will find in math that ratios are a lot better than decimals. And improper fractions are a lot better than proper fractions. So I'm never converting this. Well, I shouldn't say never, but that's the same as minus 6 2/3. But this is a much more valuable answer. I'm ready to do whatever they need me to do with that number. Whereas if I needed to do more stuff to that number, I would have to first convert it to an improper fraction. So I want my answers in improper fractions, or the perfect answers. Not even, notice that if I write it as a decimal, well then I necessarily have to round it off. That's rounded off. Not as accurate as minus 6 2/3 or minus 20/3. And it might seem like a subtle difference, but the biggest difference is that if you do the problem manually, you get this. If you do it in your calculator, you get this. So that's how I knew you were doing it in your calculator, was you gave me a decimal answer. Now, the fact is that either one of those is going to work. If we go back up into our original equation, this one right here, that answer satisfies the equation, and so does this answer. And you have to be a little bit careful when you come up with two answers. You generally should check to make sure both answers work. There are certain things that tend to give you extraneous answers, okay? Radical signs are one, absolute value signs are another, and logarithms are a third. So if you're solving equations that have any of those three in it, and you get multiple answers, make sure you check both answers. Very frequently, one of them will not work, and it's called an extraneous solution. All right. Second one. Do you prefer problems like this, or do you prefer the word problems?
Problems like this.
Yeah, me too. I was just curious if I was unique. Now, what I don't like here immediately is it's ambiguous. Is it the 1 that's being taken to the 2x plus 4, or is it the 1 over e that's being taken to the 2x plus 4?
No, 1 over e.
Which means they should have put a parenthesis there. Because the way they gave you the problem, it could be just the 1. That 2x plus 4 normally does not apply to the denominator unless there's parentheses around it. But I have no doubts that they meant to put parentheses. Now what can I do? The key to solving this is to make sure, well, how should you write 1 over e? What's another way to write 1 over e? E to the minus 1.
Okay.
And the advantage of doing that is now I can apply the rules of exponents. So what's that equal to?
E of negative 1 to 7.
Well, you multiply exponents. Whenever you have double exponentiation going on, you multiply exponents. So the left side now becomes that. The right side never changed. But notice now I have the same base on both sides. Therefore, what can I say? If I've got e to the one exponent equals e to a different exponent, what can I say about the exponents?
That negative 2x minus 4 equals 7x.
Yeah, they got to be equal. There's no other possibility. In other words, when I have base to a equals the same base to x, then I know a equals x. No matter what the base is. In this case, the base is e, but it could be anything. As long as the bases are the same and the exponents are different, then you can equate the exponents. Solve this for me. What's the next line I should write?
Negative 4 equals 9x.
And x equals?
Negative 9 over x.
Negative 4/9.
Alright, yeah.
I've seen you make that mistake once before. Is it just a verbalization mistake? In other words, you would always write it that way?
No, I just got confused.
Okay. All right. Make sure that last step, and that last step is the simplest of all steps when you're solving an algebraic equation. In other words, it's just dividing both sides by the coefficient of x. Okay, let's look at number C. 1/2 x plus 2 squared plus 3 equals 5. Work me through this equation. Should take 3 minutes. That's how much time we have.
Okay, so you subtract 3
Okay? What next?
times 2 by 2.
What next?
Take the square root of both sides.
So what's the next line read?
X plus 2 squared equals 4.
Well, okay. But you said take the square root of both sides. Now give me the next line.
X plus 2 equals 2.
No. Whenever, you just made the mistake that 90% of my students make. Whenever you are solving an equation by taking the square root of both sides, make sure your answer always begins with the words plus or minus.
Okay.
Okay? And it's not trivial. It's a different answer. Notice now, what are the two answers for x?
X equals 0 and X equals -4.
Notice that if I had not put the plus or minus there, I would have got x equals 0 only. So by putting the plus or minus, it produced the second solution. That's why I say it's not trivial. In other words, it's not, you're going to lose points if you don't put that plus or minus there every time.
Okay.
And it's something that's just really, really easy to forget. And boy, I wish I had a song like, the ABCs, where I could tell people, whenever you're solving an equation by taking the square root of both sides, start your answer out with the words plus or minus. Nicholas, it's been a fun 3 sessions this week.
Yeah.
We didn't quite get through this. How far did we get? We got through 16, and there's another 23. 1 or 2 more sessions might do it if you want to finish this paper.
I think I can finish it on my own,
Okay,
I think.
that's fine. Yeah, no, I'm not trying to push you. I was just giving you an estimate. Some of these problems are a little tricky, like the cube root of the square root of 5. How would you do that, just in the minute that we have left? How would I do this problem right here? Convert everything to fractional exponents. In other words, square root of 5 is 5 to the 1/2. And then the cube root of 5 to the 1/2 is 5 to the 1/2 to the 1/3. Now you can apply the rules of exponents and you get 5 to the 1/6. That's what that thing simplifies to. The 6th root of 5. All right. Nicholas, I'll let you go, and I will talk to you next time.
Thank you.
Bye-bye.